we finally have enough context in molecular orbital theory to confront a real organic molecule. So what I want to do is acetylene. C2H2, which is a common gas used in oxyacetylene welding, and has a Lewis structure as follows: a triple bond between the two carbons and a hydrogen on each end. So it's a linear molecule, so we're not going too far yet. And we're going to use what we already know about C2 dimer, and we're going to use what we learned in the molecular orbital theory for beryllium hydride and couple those together. So we're going to treat this as a ligand group of two hydrogens with a central atom of the C2 dimer. So effectively what we're doing is the same kind of thing we did with beryllium hydride, but instead of just putting a single beryllium atom down into the center of those hydrogen ligand groups, we're going to put the C2 dimer. We already know what the ligand groups look like. And the ligand groups we're going to create for acetylene are identical to the ligand groups we created for beryllium hydride, where the two hydrogens in lambda 1 are in phase, and the two hydrogens in lambda 2 are out of phase. So it's lambda 1 with Gerada stereochemistry, and it's lambda 2 with ungerada stereochemistry. And we'll use that, along with the symmetry of the orbitals for the carbon dimer, to limit the number of possible combinations and make it easier for us to work with. So the two carbon nuclei are in here, separating the hydrogen 1s orbitals from each other by a large enough distance that within the 90 or 95% probability surface, there's no actual overlap between the hydrogen 1s orbitals, and it just looks like the individual 1s orbitals. So those ligand groups are made for the two hydrogens, and now we have to know what C2 looks like. And we know that C2, because it's one of the elements to the left of nitrogen, nitrogen to the left, has sp mixing, which means it takes the fiddle-shaped orbital energy diagram where pi y and pi z are below sigma 3g, so it looks like that. Got our violin-shaped orbital energy diagram, and there are 8 electrons in C2 dimer. So we have sigma 1g and sigma 2u, anti-bonding sigma 2u orbital filled, and then we have the pi bonding orbitals filled with sigma 3g. So here's our frontier, if we cared, with the HOMO being the pi bonding orbitals, and the LUMO being sigma 3g. That won't be important from the perspective of creating the orbital energy diagram for acetylene. We know that because each hydrogen brings 1 orbital and each carbon brings 4, there will be 10 total molecular orbitals. And we know that because it's a linear molecule, the two 1s orbitals, the two 2s orbitals, and both of the px orbitals will be along the bond axis, it's the x-axis. So there'll be 6 sigma orbitals. And there'll be 4 pi symmetry orbitals. Pi symmetry orbitals won't actually look any different than they would for ordinary C2 dimer, because hydrogen doesn't have any orbitals with pi symmetry. So these pi star orbitals and these pi orbitals will come come over unchanged when we insert the C2 dimer into the middle of the hydrogen ligand groups. We know that sigma 1d is a great big fat orbital with little electron density outside away from the other nucleus because of the sp mixing. We know that sigma 2u has the vast majority of its electron density outside the nuclei because of the sp mixing. It's less effectively anti-bonding and has a single node. We know that sigma 3g has a lot of electron density outside and a small node in the middle. And 2 nodes. Because sigma 1g increases the electron density between the nuclei, sigma 3g increases the electron density outside the nuclei. So the shape is different, it's opposite as it would be with no sp mixing, where the inner lobe would be bigger than the 2 outer lobes. And then now we know that sigma 4u, because sigma 2u has very little electron density between the nuclei, sigma 4u will have large lobes between the nuclei and smaller lobes outside. 3 nodes. Notice that the 2 anti-bonding orbitals have nodes between the nuclei, whereas the bonding orbitals do not. Neither of these 2 bonding orbitals has a node between the nuclei, so the electrons can get between the nuclei if they want to. So these are the 4 sigma symmetry orbitals that we're going to have to combine with these 2 ligand groups to create the sigma framework, the 6 sigma orbitals that we have for acetylene. Meanwhile, we will still have pi y and pi z, which will look identical except rotated 90 degrees. And we still have pi star y and pi star z, which are those kind of stretched cloverleaf. One lying in the plane of the board, and the other one, pi star z orbital, over here, lying outside or lying perpendicular to the plane of the board. And those orbitals are going to look exactly the same as they did. So we can actually bring them over if we want to and put them in the relative location that they're going to be. Pi y and pi z, and pi star y, and pi star z. Those orbitals are going to be at exactly the same energy that they were before we dropped the C2 dimer into the ligand group. So now we need to classify the orbitals as either Garada or ingarada with respect to reflection through the plane perpendicular to the bond axis bisecting the molecule. This one is Garada because the sign on the orbital will not change as we reflect it, and this one is ingarada because reflection changes the sign. Positive lobe reflects into the negative. So we can combine sigma 1g and sigma 3g with lambda 1. And we can combine sigma 2u and sigma 4u. So we have a situation that's similar to what we had with the unsymmetrical diatomic hydrogen fluoride, where we have 3 orbitals that are going to combine to form 3 new orbitals, but we have 4 possible combinations of those orbitals. We have possibility of sigma 1g plus lambda 1g. We have sigma 1g minus lambda 1g. We have sigma 3g plus lambda 1g. And we have sigma 3g minus lambda 1g. There are 4 possibilities, but only 3 orbitals. And similarly, we have 4 possibilities with the combination of the lambda 2u with the sigma 2u star. We have both constructive and destructive interference versions. again, they need to make just 3 orbitals. So in 2 cases, we have 4 possible combinations making only 3 orbitals, which means that we must have a degenerate set of solutions. And it's the same situation as it was with hydrogen fluoride, where the anti-bonding interaction with the lower energy sigma orbital gives the same predicted orbital as the bonding interaction with the higher energy sigma orbital. So sigma 1g minus lambda 1g is degenerate with sigma 3g plus lambda 1g. And similarly, sigma 2u star minus lambda 2u is degenerate with sigma 4u star plus lambda 2u. So we actually only have 3 different orbitals predicted: constructive with the lower energy sigma orbital, destructive with the higher energy sigma orbital, and then the degenerate set. Constructive with the lower energy sigma anti-bonding orbital, destructive with the higher energy sigma anti-bonding orbital, and then the degenerate solution. So all that remains now is to figure out what these 6 different unique combinations lead to in a prediction as to what the shape of the orbital will look like, how many nodes there will be, and then where they're likely to lie on the energy diagram. So let's take the set of bonding molecular orbitals from the C2 dimer, sigma 1g and sigma 3g first, and consider the new order. So sigma 1g, big fat orbital. Sigma 1g is a big fat orbital. We're going to drop that inside the hydrogen, which is in phase. Everybody's going to be nicely in phase, and we're going to get bulges here, so that when we're done, this orbital is going to be a large orbital. We'll still have around symmetry, and it will delocalize those electrons over all 4 nucleus. That's always the most stable orbital. The most stable orbital for any molecule is going to allow the 2 electrons in to interact simultaneously with all 4 nuclei. The electrons are happier, the more nuclei they're interacting with, so that's always the lowest energy situation. And we can put that down here. There's sigma 1g, much lower than pi bonding orbitals. Because of the pi bonding orbitals, not only are you only interacting with 2 nuclei, but you're not even between the 2 of them, right? In the internuclear space where you really want. Sigma 1g minus lambda 1g would involve changing the sign on the ligand group orbital, and we would now create a new node. We chop out some of this electron density here, creating 2 new nodes, and so we're going to have something that actually has, well, it's going to be sigma 3, in fact, because there are 2 nodes, and is anti-bonding with respect to both carbon-hydrogen bonds, even though it's still bonding with respect to the carbon-carbon bond. So that orbital, when you're done, will look like this. Notice that those orbitals that used to be spherically symmetrical bound with the hydrogen nucleus are now not, because we removed some of that interior electron density. And then in the middle, we'll have what's left of this. We'll have what's left of this plus orbital, bonding the 2 carbon nuclei together, where it didn't before. Sigma 3g. There's going to be a single node orbital that will lie in between these 2. So if I put sigma 3g here, I know that there's going to be a orbital in between those two that has just one node. But it's going to come from the combination of the Ungerada orbitals. And as we continue to go up in energy, we will continue to increase the number of nodes. So I'm now actually in a position to write the remainder of the orbital energy diagram because I know that the sum of all of the orbitals has to equal the sum of the orbitals they came from, which means that there must be a sigma 4u orbital about the same distance from the pi star orbitals as sigma 3g is from the pi orbitals. There's going to be a sigma 5g orbital up here. I shouldn't say it's anti-bonding because anti-bonding and bonding don't really have much meaning anymore because it depends on which nuclei you're talking about. In a situation where bonding with respect to the CC bond, but anti-bonding with respect to the CH bonds. And then there must be a sigma 6u up here about the same distance away from the pi star as sigma 1g is. And we know that they will have 3 nodes, 4 nodes, and 5 nodes respectively. I could even put the electrons in if I want to. I know that there are going to be 10 total electrons, 1 from each hydrogen and 4 from each carbon. And so I will fill these orbitals here, half filling the pi y and pi z before I completely fill it. And my frontier will be the pi system. My HOMO will be the pi bonding orbitals. My LUMO will be the pi anti-bonding orbitals. And that is a really convenient observation. Because what that means is if you want to predict reactivity for acetylene, you don't actually have to do any of this sigma framework that we're working on here, because the frontier is the pi system. And the pi system is much easier to put together than the sigma system, because the pi system only involves 2 central carbons. That's a general truth when you're working with hydrocarbons, double bonds, or triple bonds, things that only contain hydrogen and carbon. Always the pi system is the frontier, which means you really only have to worry about what the pi orbital and pi star orbitals look like if you want to see how things are going to react. But we want to see what the rest of the picture looks like. We made sigma 1g and sigma 3g, which have 0 and 2 nodes respectively. Probably you can predict the sigma 5g, which is this interaction, will end up having 4 nodes. It's the other Dorada orbital. And so what we're looking at is sigma 3g interacting destructively with lambda 1g. So the sigma 3g orbital that we're looking at here looks like that. Positive lobe on the outside, negative lobe on the inside. And that's going to interact destructively. So we've got the negative sign of the wave function for the lambda. I have the 2 existing nodes, but then I'm also going to create new nodes here where there's destructive interaction. So there'll be a total of 4 nodes. Two of those nodes, the new ones, are between the hydrogen and carbon nuclei. The other 2, the existing nodes, go right through the center of the nuclei, just like they did here. And so we've got smaller lobes here now than we used to because some of that electron density was moved. And we've got the asymmetry that we would expect. And there's our 4-node orbital. Right? It's symmetric. Right? We've chopped it up symmetrically so that the orbital reflects into itself nicely. So this is sigma 5g. The other combination that I didn't draw would be sigma 3g plus lambda 1g. So what that would look like would be constructive interference here in a bulge and 2 nodes, just like this one. The nodes are in slightly different location because this one would predict that the nodes are between the nuclei and This one would predict that the nodes are actually on the nuclei, but effectively this is the same orbital. It's a two-node orbital. So each solution, the reality is somewhere in between. So the nodes won't exactly go through the nuclei as they do in sigma 3G, but they won't be exactly between the hydrogen and carbon nuclei as we might predict from the other interaction. But it'll still be a two-node orbital. We're still predicting basically the same thing. So we know what those orbitals will look like. And we know where they are on the energy diagram. Now what we need to do is look at the combinations of the anti-bonding orbitals. So we want to do sigma 2u star plus lambda 2u. Sigma 2u star looks like this. And lambda 2u like that. There's a node for sigma 2u star. We now have constructive overlap and a bulge. We're going to get a single node orbital, sigma 2u. It's going to look like this. It's bonding with respect to the carbon-hydrogen bonds, and it's anti-bonding with respect to the carbon-carbon bond. So it's kind of a bonding orbital. This one's bonding with respect to all, the carbon-carbon bond and both carbon-hydrogen bonds. Sigma 2u is bonding with respect to the carbon-hydrogen bond, so anti-bonding with respect to the carbon-carbon bond, and sigma 3d is bonding with respect to the carbon-carbon bond, but anti-bonding with respect to the carbon-hydrogen bond. When we get to the top, we might expect to see an orbital of anti-bonding with respect to everybody. So this is the sigma 2u star plus lambda 2u. Sigma 2u star minus lambda 2u. It will look like this, where we change the sign on the ligand group orbital. We're going to create two new nodes where there's destructive overlap in both cases. And we will end up with an orbital that already had the node here between the nuclei. Sigma 4u. We already had the node between the nuclei, and now we're creating new nodes between the carbon and hydrogen nuclei. So it's going to look something like that. So this one is anti-bonding with respect to all of the bonds, both carbon-hydrogen bonds and the carbon-carbon bond. The last different combination will be sigma 4u star minus lambda 2u. That's going to interact destructively with the hydrogen orbitals, thus creating two new nodes. But it already had three nodes, one between the two carbon bonds, or the two carbon nuclei, and one through each carbon nucleus. So it's a total of 5 new nodes. Not only is it anti-bonding with respect to all of the different possible combinations of atoms, but it also has the extra 2 nodes. And it will look like this. We'll still have those 2 big lobes in the middle, the phase. New nodes are here. The existing nodes are here. total of 5 nodes, and that's my sigma 6 U orbital. You'll notice that you could actually have predicted what the various sigma orbitals would look like by just taking this giant sausage and gradually chopping it into smaller numbers of pieces. So to go from sigma 1G to sigma 2U, all you have to do is slice it in half, right? And you have 2 lobes instead. Slicing it into thirds gives you sigma 3G and 3 little lobes on your sausage. Slice it in half, and then slice each of those in half, that gives you sigma 4U. Slice it into 5 kind of equal segments to sigma 5G, and then slicing it in 5 places to give you sigma 6U. So it's very much like a sausage that you're just twisting, or a balloon. You can take a long balloon and twist it in the middle, you have sigma 2U. And if you twist it twice more, then you have sigma 4U. If you twist it just twice, right, on the thirds, you have sigma 3G. So it's possible to predict what the orbitals are going to look like without going through all of what I just went through here. For completeness, let's look at what sigma 4U star plus lambda 2U would look like and confirm that it predicts the same orbital that we predicted by taking sigma 2U star and subtracting sigma 2 or lambda 2U. So we should predict this orbital, or something that looks very much like that orbital. With constructive overlap. We get a little bit of a bulge here. You'll notice we don't create any new nodes when we do this sigma 2U star plus lambda 2, or sigma 4U star, sorry, plus lambda 2U. Right? We don't predict any new nodes, but we already had 3. And once again, we're predicting a 4-lobe orbital just like the 4-lobe orbital we predicted here. The actual locations of the nodes varies a little bit. Here we have those nodes from sigma 4U star that came exactly through the nuclei, which is not what we're predicting here. So the truth is somewhere in between, but it still has 1 node right in the center between 2 carbons, and then 2 nodes kind of in between the carbon and hydrogen, probably closer to the carbon than to the hydrogen, because this prediction will put them right on the carbon. So it's a fairly simple organic molecule, and we're aided by the fact that it's linear. Right? So a linear molecule is simpler than if we went into something that exists in a plane in 2 dimensions, or something that exists in 3 dimensions. It's almost impossible to draw the results of something that happened in 3 dimensions. So that's the last linear molecule I want to talk about. And there will be a couple more videos where we talk about what to do when you go into a molecule that now has 2 dimensions, that lies in